Have you ever wondered what it would be like to journey into a black hole, one of the most mysterious and terrifying objects in the universe? If you have, then welcome to our exploration of this fascinating cosmic phenomenon. Black holes. Their very name evokes a sense of wonder, curiosity, and perhaps a tinge of fear. They are regions of space where gravity is so intense that nothing, not even light, can escape their pull. This gravitational clout is due to an immense mass condensed into an incredibly small space. In essence, a black hole is a point in the universe where the fabric of space and time becomes infinitely distorted. Scientifically speaking, black holes are the end product of the death of massive stars. When such a star has burned out its nuclear fuel, it collapses under its own weight, causing a supernova explosion. What remains is a core with gravity so strong that it warps space and time around it, creating a black hole. But what makes black holes so intriguing is the enigma that surrounds them. Their existence was first proposed as purely mathematical constructs by Albert Einstein's general theory of relativity. It wasn't until decades later that we found observational evidence to support their existence. And yet, despite our advancements in technology, we still know surprisingly little about what lies within these cosmic beasts. What happens when you fall into a black hole? What's on the other side? Could they be portals to other universes or dimensions? While we don't have all the answers, we can use what we know about physics to make educated guesses. With such immense gravity, black holes undoubtedly have some peculiar properties. Let's explore them. According to Einstein's theory of general relativity, black holes possess incredibly potent gravitational fields. These gravitational fields are so powerful that they warp the very fabric of space-time around them. Now, what does that mean? Well, imagine space-time as a rubber sheet. When you place a heavy object on the sheet, it dips and curves under the weight. That's exactly what black holes do to space-time. Now, this warping of space-time has some fascinating consequences. One of the most mind-boggling is the phenomenon known as time dilation. Simply put, time dilation is the difference in elapsed time measured by two observers due to a velocity difference relative to each other, or by being differently situated relative to a gravitational field. It might seem like a plot from a science fiction movie, but it's a scientifically proven fact. The stronger the gravitational field, the slower time passes. This means that time actually slows down near a black hole. Let's put this into perspective with a thought experiment. Imagine if you could hover near the edge of a black hole in a spaceship, while your twin sibling stays back on Earth. Time would pass slower for you near the black hole compared to your twin on Earth. By the time you return, you might find that your twin has aged more than you have. This is not because of any cosmic skincare routine, but because of time dilation. The concept of time dilation challenges our everyday understanding of time. We are used to thinking of time as a constant, unchanging entity, but in the vicinity of a black hole, time becomes a malleable quantity, stretching and compressing under the influence of gravity. In essence, time near a black hole slows down, a phenomenon that truly defies our everyday understanding of time. So the next time you complain about not having enough time, remember, a quick trip to a black hole might just give you all the time you need. Light, the fastest thing in the universe, meets its match when it encounters a black hole. These astronomical anomalies are so powerful that nothing, not even light, can escape their gravitational pull. Imagine light as a sprinter at the starting line, ready to race. But instead of a finish line, there's a black hole. When the starting gun fires, light shoots forward at a staggering speed. But as it nears the black hole, it finds itself not crossing a finish line but rather being pulled backward. This is due to the event horizon, a boundary around a black hole where the gravitational pull becomes too strong for anything to escape. Imagine it as a point of no return. Anything that crosses this line, including light, becomes irretrievably lost inside the black hole, swallowed by the cosmic beast forever. In the face of a black hole, light is no exception to the rule of inescapability. Did you know that black holes emit a certain type of radiation known as Hawking radiation? This radiation isn't like your everyday radio waves or microwaves. It's a special kind of energy that is produced right at the edge of a black hole, a boundary we call the event horizon. As you might guess, the event horizon isn't a place for a casual Sunday stroll. It's the point of no return for anything that ventures too close to a black hole. And it's here, in this extreme environment, that Hawking radiation is born. But what's interesting is that this radiation is associated with the temperature of a black hole. You might think black holes are cold, dark, and devoid of any heat. But that's not entirely true. Each black hole, no matter how large or small, has a certain temperature. And it's this temperature that gives rise to the Hawking radiation we just talked about. So we've got temperature covered. But what about gravity? Well, the gravity near a black hole isn't your garden variety gravity. It's incredibly strong, to put it mildly. In fact, it's so strong that it affects everything around it. If you were unfortunate enough to get too close to a black hole, you'd feel this gravity in a very real, very uncomfortable way. As you approach the black hole, the gravitational force becomes so strong that everything disintegrates and stretches out. This isn't your typical stretch like pulling a piece of gum or taffy. We're talking about stretching on a cosmic scale, a process known as spaghettification. Yes, you heard that right. In the vicinity of a black hole, you'd be stretched out into a long, thin strand like a piece of spaghetti. No, it's not a pleasant thought. But it does give us an idea of just how powerful and mysterious these cosmic entities are. The laws of physics as we know them seem to warp and twist in the presence of a black hole's formidable gravity. Imagine approaching a black hole. What would you see? What would you feel? As you edge closer to the black hole, the very fabric of space and time becomes more and more distorted. This is due to the black hole's incredibly powerful gravitational pull, which bends and warps space-time around it. This intense distortion means that light, the fastest thing in the universe, can't escape the black hole's grip. This leaves us in the dark, unable to see what's happening around us. All we would see is the event horizon, the boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. But what would it feel like to approach a black hole? Well, the experience would be quite literally crushing. The gravitational pull of a black hole is so powerful that it would stretch and squeeze you into a thin strand, like a piece of spaghetti. This process is known as spaghettification. As you get closer and closer to the black hole, the difference in gravity between your head and your feet would become so great that you would be stretched out long and thin. At the same time, the intense gravitational force would compress you horizontally, making you thinner and thinner. Now, this is not a pleasant experience to imagine. The intense gravity would rip you apart before you even reach the black hole's event horizon. But don't worry, this is all theoretical. In reality, you wouldn't be able to get close to a black hole without being torn apart by the extreme gravitational forces. While venturing into a black hole is a journey with no return, understanding these celestial enigmas helps us expand our knowledge of the universe. As we continue to study black holes, we delve deeper into the mysteries of the cosmos, revealing fascinating insights about the nature of space, time, and gravity. Black holes, the universe's enigmatic and fearsome entities, continue to pique our curiosity. We've journeyed through the mysteries of these cosmic chameleons, uncovering their extraordinary effects on time, light, temperature, and gravity. Our foray into the realm of relativity has shown us how time can slow near a black hole, a phenomenon known as time dilation. We've seen light, the fastest thing in the universe, unable to escape the black hole's event horizon, forever trapped in its gravitational clutches. We've delved into the paradox of Hawking radiation, where these seemingly cold, dark entities emit a temperature. We've also explored the immense gravitational pull that can stretch anything into long, thin shapes, a process aptly called spaghettification. Although we can only speculate what we might see or feel near a black hole, the journey has undoubtedly been a fascinating one. Although traveling to a black hole remains a far-fetched idea, exploring these mysterious entities through this video has hopefully augmented our understanding of the workings of the universe.